In this problem, we're going to solve multi-headed attention. And again, the first thing I want to say is that I highly recommend you solve single-headed attention before we solve this problem. As if you understand single-headed attention, this problem is not that hard. It's actually kind of easy. Single-headed attention, on the other hand, which this problem builds on, is a lot harder just because there's so many new concepts introduced in that problem. So we're going to assume that you've kind of solved that problem, and then this problem isn't going to be that bad. Though we'll still generally explain the idea of attention, but we won't go into as much detail as we did in the single-headed attention video. So the problem statement says that this layer is actually what makes LLMs so good at talking like real people. So single-headed attention is pretty good, but when we do this whole multi-headed thing, which we're going to explain in this problem, that's what made like the latest transformer neural networks way better at chatbots that you might have seen in previous years. And I've also made an explanation video of the concepts if you would like to watch that as well. So we have to code up the multi-headed self-attention class and then the single-headed attention class. Essentially, the solution code for that is going to be given in the starter code for this problem, and we're going to actually make instances of this class to solve the multi-headed attention problem. And we're told that the forward method needs to return a b by t by attention dim tensor. So actually returning the tensor of the same shape as the single-headed attention problem. And we're going to be given embedding dim. That's our first input, and this is actually something that we were also previously given in the previous problem. We're also given attention dim. We're given embedded, which is b by t by e. And this was also given in the previous problem. However, this is our new input that we really need to pay attention to, the num heads. This is the number of times that we're going to make an instance of the given self-attention class. And we have this constraint that attention dim mod num heads is 0. So attention dim is a multiple of num heads. And there's an example here. The numbers are not going to make a ton of sense, but it does help us understand the shapes. Our input is supposed to be b by t by e. That's the shape of embedded, and we can actually infer that the batch size is 2 here. The t, or the context length, is also 2. You can infer that from this example over here. And then e, we can find that e is 2, and that makes sense as well, given that we have a 2 by 2 by 2. We have two different 2 by 2s in our input embedded. And if attention dim is 3, and the b and t are supposed to remain the same, then we have two different 2 by 3s. So it's a 2 by 2 by 3, and that is exactly what we have over here. So the shapes do make sense. So what actually is multi-headed attention? So we take an instance of single-headed attention, SHA, and previously we were passing in our input, the b by t by e input, and whatever single-headed attention returned was the output. However, now, depending on what that num heads parameter is, whatever that is set to, we'll make that many instances of self-attention and have them operate in parallel. So let's just say num heads was 3. Then we have 3 over here. And what we'll do is whatever our input was, that b by t by e input embedded, I'm just going to simplify that to x for now. Let's pass x. Let's actually pass x in to all of our heads of self-attention. If I had a fourth one over here, it would also be passed in there. And then what we'll do is we'll just concatenate all of these outputs together, the outputs of each head. So each head of self-attention, each of these boxes over here was able to operate independently and process X and obtain a different output, right? Because each of these layers of the neural network have different, if they're separate instances, they have different weights, right? They're learning different keys, queries, values in those linear layers that make up the single-headed self-attention, and ultimately they're going to generate something different since, again, they have different numbers, different weights, they're trained separately, even if they're given the same input. So we're going to then concatenate all their outputs together. We can call this the concatenated version, and that is what we would return from the multi-headed attention forward method. And that's it. So then when we have the transformer neural network architecture, and remember we're getting pretty close to coding up this full GPT class, we're actually then going to use the multi-headed attention class as a layer in this neural network. So then that's going to become one of our building blocks for this giant block over here, which is called the transformer block. So why does this actually work better than just single-headed attention? Because remember that attention dim, which we can call A, mod num heads is 0. So for each head, we're actually making the size of each head, or the attention dim parameter, when we instantiate that single-headed attention object for each of those heads, we're making each of them have a head size of A, essentially floor divide num heads, whatever this integer is. So our total number of learnable parameters in the neural network isn't changing, right? If I were to do just one head with an attention dim of A equals 64, and the other option is to maybe do 8 heads, and for each of them set A equal to 8, then the total number of learnable parameters in the neural network hasn't really changed, even though we're having multiple heads that are each operating in parallel, right? Each of them gets to process the input, process that input called embedded, and learn parameters, albeit each head is learning less parameters than if we just had one giant head. So why does this actually yield better results? Because the general trend is more parameters, bigger model, the model can learn a more complex relationship, and we get better results. Well, even though each head has less parameters than if we had one massive head, it turns out that each head gets to learn something different because our input X is independently passed in to each head. So each head independently gets to learn something different. And what we actually find when we see how the heads and those weights get activated based on different inputs is that researchers have found that you'll actually have one head that might specialize in focusing on or attending to the next token. One head that really specializes on focusing or attending to, right? This is all about which parts of the input do we pay attention to, the direct objects of verbs. One head might specialize in indirect objects of verbs. So we know that for a model to truly understand language, it needs to understand grammar, right? It needs to understand the structure of the language and how all the words are put together, or how all the tokens come together. So we actually find that each head specializes in maybe a different grammar rule, and this seems to be why this is boosting the performance of the neural network, rather than just having one head that's responsible for learning all the rules of the language. Okay, now let's jump into the code. So the first thing we need to think about is that we know we're going to have a bunch of instances of this given single-headed attention class. So we're probably going to need to store those in some kind of collection in our constructor over here, right? But it turns out that any instance variables of a class that is a subclass of nn.module, and this multi-headed self-attention class is a subclass of nn.module, any instance variables need to also be neural network parameters. So if I did something like this, self.heads, and then made it a normal Python list, this is going to throw an error when we're using PyTorch because of the restriction that I just mentioned. So there's actually a class called nn.modulelist. So I can say self.heads is nn.modulelist, and it works just like a normal Python list. You can append to it, but it actually is restricted to only store other modules or neural network layers. So then we can say something like for I in range of num heads, we can actually then append those instances. So self.heads.append, and we can instantiate here. So self, we have to do this for these inner classes. We have to refer to it as self. So self.single head attention, and we have to pass in the embedding dim, but then the attention dim for each head is just the size of that head. And we know that should just be attention dim, floor divide, num heads. So now we have all our heads defined. Now we just need to actually write the forward method, actually get all those outputs, and concatenate them together. So we can go ahead and make a list for all our outputs. We can say outputs is just some list. And then we actually want to call the forward method of every head of single-headed attention. So we can actually just say something like for head in self.heads, and we can append to this list. So outputs.append, and it would just be head.forward, or simply just to use the default call. So head of embedded. And now it's just about concatenating those together, right? So we can say concatenated is torch.cat, And torch.cat expects two things. The first thing it expects is a collection of the things to concatenate. So our collection here will be a list, the list outputs, and it expects a dimension, something like 0, 1, 2, etc. So if we think about what the size of each thing in outputs is, right? Each element in this list is b by t by, let's call it head size, right? Because that would be the output dimension from each head of attention over here. And we want to concatenate them along this last dimension so that when I concatenate them all together, it becomes b by t by this overall attention dim that was given as a parameter in the constructor for multi-headed attention. So I would just simply say dim equals 2, or you can say dim equals -1 for the final dimension. Either would work. And then we simply round our output. So return torch.round of catted, say decimals equals 4, and we're done. And we can see that it works. So if you found this helpful, definitely leave a comment, or leave a comment if there's anything else that you would like me to go into more in depth on. Now that we have this multi-headed self-attention class done, we can just use this as a layer when we code up the transformer block in the next problem. So definitely check that one out next, as it's our next step in getting closer to having a working GPT all the way from scratch.